Let's wait for 2 3 minutes. Okay, start. So this is the last week, that is week 9. We have already uh, have taken a class on Saturday. So this is the week 9 problem solving session on mathematical methods. So today the plan is the last part of the week 8 content. That is, we will see that how ODEs, that is ordinary differential equations, can be solved using power series method. We'll see this. The next thing is that we will talk about the Frobenius method. This is another. This is also based on the power series only. So these two methods we will see. We will solve as much as questions as we can. But these are lengthy questions. These are lengthy solutions, which has lengthy solutions. So it will take some time. Means small number of questions, but it will take a huge amount of time. So this we will see in detail. And also we will start with where we have stopped in the last class, where I have to see the Green's function. That's why with the Green's function, we will try to solve one more question about the ordinary differential equation. So that is what is our plan is. Okay. So in the beginning, therefore, let's do a question on how we can apply the Green's function to find out the solution or the particular solution, particularly of the ordinary differential equation. We have already seen that in the last class. We have gone through two problems on this, but this is another, and we will end up that part. Okay. So, suppose you have a differential equation. This is another example, example 3. So you have y double dash. Just a minute. Okay. So you have, suppose a question like this: y double dash plus y is equal to 2 cos x. This is the question which is there. Okay, and with the initial condition, set of initial condition, that is y of 0 is 0 and y dash of 0 is 0. We're taking it a very simplistic condition. So what will be its complementary solution? So if we try to find out the complementary solution, then this is an inhomogeneous ODE. We can see it clearly because we have a forcing function here. But if it is not there, then we can find out the complementary solution. So just put y double dash plus y equal to 0 and try to find the auxiliary equation. And we know we have solved it so many times. So we generally assume this y is equal to some e to the power alpha x. And so if we just put it in this particular equation and put this equal to 0 instead of 2 cos x, that is how we find out the complementary solutions. And that is what we will be doing here. So the auxiliary equation will be, so it will be alpha square, and there is no first order derivative, so alpha square plus 1. That should be equal to 0, right? So alpha will be equal to plus minus root of minus 1, which is nothing but iota. So this is very well known. It signifies some kind of an oscillatory solution, that is either y will be some c1 sin x plus c2 cos x. This is how we can write it. So what we will do is that we will assume that, let us say, y1 of x is nothing but sin x and y2 of x is equal to cos x. Okay, assume, we assume this is the, these are the y1 and y2, so that we can, if we can add, like y is equal to c1 y1 plus c2 y2, which we can write based on the superposition principle. Fine. So this is now done. Now we need to find out the particular integral or particular solution, because it's an inhomogeneous equation. So particular solution is required. So how will you find out particular solution? There are so many ways to find out particular solution we have discussed. One is the superposition principle itself. It can be used by equating that with some kind of a coefficients and calculating the values of the coefficients. That is number one. Number two is that in case of you have a set of rules to find out the particular solution, which we have seen based on some, uh, suppose b square plus something is there. You know that for each of the what you call as differential equation, there is a set of rules, or based on the forcing functions, there is a set of rules. We have seen that. And the number three is this one. Okay, this is the Green's function. Using Green's function to find out the particular solution. So we will be using here the Green's function. This is the last thing which we were discussing in the last class, and we have solved also two questions. So this is the third example, and yeah. So how to find out the particular solution? I will do it using Green's function. Okay. So how will we define the Green's function? This is the simplest way of solving for the particular solution, is that you take y1 of t. This t is some kind of a dummy variable, okay, and this is y2 of x minus y2 of t and y1 of t, and it is divided by the Wronskian, that is w of t. So W of t, the Wronskian, is can be written as y1t, y2t, and you have y1 dash t, that is first order derivative with respect to t, and y2 dash t. So any function, it is in terms of x, and I have told you that this t is the dummy variable. So just replace x with t and try to solve this W of t. So we replace y1t sin x as sin t. This becomes cos of t. Differentiation of sin t is cos t. Differentiation of cos t is minus sin t. Right? This is done, and you have to perform the determinant. You have to calculate the determinant. So what it will be? Minus sin square t minus cos square t. That gives you minus sin square t plus cos square t. Right? This gives you minus 1. Alright, so this is the so Wronskian is calculated, and it is a constant function. We can see it. Now we have to calculate the Green's function here. So how to do it? It's already been defined. So g of x comma t, y1 of t, which is we have assumed y1 as sine, right? So it will be sine of t. Then y2 of x, which is cos of x, minus cos of t, because it is the y2 of t now, and this is sine of x, and divided by the Wronskian, that is minus 1. So we can write g of xt, instead of writing minus 1 in the denominator, let us multiply minus 1 throughout in the numerator. So it will be something like this: cos t sin x minus sin t cos x. So what it will be? You can clearly see that we can write it this in terms of sin a minus b, sin a cos b minus cos a sin b. Right? So this can be written as sin of x minus b, right? Because sin of a minus b is nothing but sin a cos b minus cos a sin b. That's all. That is what we are doing. So we can write this function as sin x minus b. And then how to find out the particular solution? Very simple. You have to write yp of x will be equal to start from the so it will be from the x node to some x. This is the initial condition, and this is the some final value x. Okay, you have to write g of x comma t into f of t. If this is the forcing forcing function, where you will find out the forcing function in the actual ordinary differential equation. So this is the forcing function f of x. So this is f of x, but I'm writing it as f of t. It's a dummy variable. You can understand. Okay, so this is how we can write, and we will write it in terms of dt. So finally, x naught, which is 0, which is given in this question, that is, yeah, it will start from 0. This is the initial point. Okay, so it is 0 here, and you can put x over here. We have found out the Green's function sine of x minus t. Now, what is your forcing function given in the question? This 2 cos x, right? So, but it has to be in terms of some dummy variable t. So that is what you will write as 2 cos t. That's all. Just replace x with t and dt. So you can see that it is in terms of some dummy variable. The integration is done with respect to some kind of a dummy variable t, and finally t is getting the value of x. That's all. Okay. So this is yp of x, and you have to now solve this integral. So how will you do it? Simple. Just open up this sin x minus t as we were getting here, right? So we will do that. So can we write this as 2 sin x cos t? One cos t is also there. So it's cos t dt minus 0 to x again, because it's an integral. You have 2, what you will have, cos x sin t and cos t dt. Right? This should be the thing, because sin a minus b is sin a cos b. minus cos A sin B. And this cos t into 2 was already there here. So now solve it. That's the simple thing. So this integral is not in x. Remember. So we can take this sin x. In fact, we can take these two outside also. So 0 to x. You have cos square t. Cos square t dt. Fine. Next one, you can take cos x. Leave 2 inside because you will understand why. Because you have a sin t and cos t. And you can know, the 2 sin a cos a is your sin 2a. So that's why we have intentionally kept this 2 in the second integral. So finally, what we can do, so this is 2 sin x. How to solve cos square t? You have to write 1 plus cos 2t divided by 2 dt. This is just a trigonometric conversion. Cos x 0 to x, and this is sin 2t dt. Great. So we have converted mostly in the trigonometric form, and we have converted in such a form that these functions will be easily integrated. So it will be 2 sin x, and you have what? So here, half is there, so it will be t by 2, its integration, and cos 2t will be sin 2t divided by 2 into 2, 4. Okay, 0 to x minus cos x sin 2t can be written as plus cos 2t because there is a negative sign which will come from the integration, right? This will be from 0 to x. Excellent, we have done it. So yp of x, these two you can chop here and write it as sin x. Now what will be the inside thing? It will be x plus sin 2x by 2, right? This can be done minus t taking the value of 0 is 0 and sine 2 of 0 is 0. So entirely it is 0 plus cos x. What will be about, what about this? Cos 2x by 2 minus cos 0 is 1. So you cannot ignore this. Great. Almost done. Yp of x will be therefore x sin x, right? Plus sin x sin 2x by 2 plus cos x cos 2x by 2 and with a minus cos x by 2, right? This is what you have. Fine. So yp of x, this becomes x sin x plus, can you take half common and write this as cos 2x cos x minus, or sorry, plus sin 2x sin x. Yes, we can write half is only taken common minus cos x by 2. Intentionally kept it outside. So yp of x will be finally sin x plus. Look at the bracketed term cos 2x cos x plus sin 2x sin x. Cos a cos b plus sin a sin b. That becomes cos a minus b. So it will be half cos 2x minus x. Remember, whenever it is negative, there is a plus inside. Okay, minus cos x and b. So yp of x, one step. So it will be x sin x plus half, what it will be, cos x minus half cos x. So this and this cancels. Therefore, finally, yp of x comes out to be x sin x. So this becomes your particular solution using the Green's function. And you already have the oscillatory solution for the given ODE. So this is how you have to proceed for any question which if you want to solve it using Green's function. Yeah, so that's another way of calculating the particular solution. Okay, so we have solved enough about the Green's function. We have already discussed in the last lecture. So you can go to the YouTube video or the notes. You will find it out. Okay. Now we will come to the power series solution of the differential equation. Okay. So next topic is the power series solution of ordinary differential equation. We are generally dealing with the ordinary differential equation only. So instead of giving so much of theory, let us take an example. Let's say you have d2y by dx2 minus y equal to 0. This is some kind of a homogeneous ordinary differential equation. Homogeneous because it is 0. So what will be the solution, the complementary solution? It will only have complementary solution, no particular solution. So what will be the complementary solution? Just take the auxiliary equations. It will be alpha square minus 1, which is equal to 0. Alpha will be equal to plus minus 1. Right? So I can write the complementary solution as c1 e to the power x plus c2 e to the power minus x. Right? This should be the solution. We know this. Now, the power series solution will be you have e to the power x and you have e to the power minus x. Can you expand this in terms of some kind of a power series? Expand in terms of power series. Okay, similarly this one. Okay, so what we will do, we know, so from our previous knowledge, we know e to the power x can be written as 1 plus x squared upon 2 factorial plus x cubed upon 3 factorial and so on. It will go to infinite. Similarly, e to the power minus x therefore can be written as 1. X is negative, right? So minus x. X squared will be always positive, but x cube will be negative. So odd powers of x will have a negative sign, even powers will have a positive sign. This is how e to the power x and e to the power minus x, they are written in terms of some kind of a power series. Okay, so in this case, if you want a power series solution, it will be something like this: c1 times, sorry, 1 plus x squared by 2 factorial plus x cubed by 3 factorial and so on, plus c2 times 1 minus x plus x squared by 2 factorial minus x cubed by 3 factorial and so on. Okay, so this should be the power series solution of the given ordinary differential equation. Now the question is that in this case, we know the solution, like e to the power x is there. If it is the sin x or cos x also, we can also write it like that, right? Sin x also can be written in terms of some kind of a power series. Cos is also written in terms of a power series. Great. If those are there, then it's good. But there are sometimes there are some ordinary differential equations which have some complicated functions. Actually, will come as a solution, right? For that, what we will do. So there are techniques to solve them, and we will see that. Okay. So mostly we will be doing uh, generally, I think, homogeneous equations to solve this power series method or the power series method. Okay. So generally homogeneous equation, we don't have the inhomogeneous one. Okay. Before proceeding into how to do the power series solution, the steps to do it, let's define two things. One is the ordinary point. Okay. One is the ordinary point. So what is an ordinary point? So suppose you have a differential equation which is of the form this, right? This is the form, and you can see that the coefficients or the constants which we generally write as a constant. This can be some kind of a polynomial. Okay, so I can write this a naught A1 and A2 are some polynomials in X, right? In some polynomials in X. Now, X is equal to A is an ordinary point of this ODE, ordinary point, if your A naught of X at X is equal to A is not equal to 0. If at X is equal to A, this polynomial is not equal to 0, the first one, okay, the corresponding to the highest order of the differential equation. If that polynomial is not equal to 0 at a particular point, then that is the ordinary point. There can be many ordinary points. Okay. The next one is the opposite definition, which we call as the singular point. One is the ordinary point. Now it comes to be the singular point. Exactly opposite. If the polynomial a naught of x vanishes, if it vanishes at x is equal to a, then the point x is equal to a is a singular point of the ordinary differential equation. Okay, so this is exactly opposite to that. So if you have your a naught x is equal to a is equal to 0, it vanishes, then this x, this point, is the singular point. Okay, this is done. Now we know from the previous concepts of the ordinary differential equation that for say second order ODE, which we are generally dealing with, ordinary differential equations, there will be two series, right? Because there will be two functions, right? Either you have y1 and y2, and the solution total means net solution will be some say y is equal to the constant times y1 plus another constant times y2. This comes from the superposition principle. Okay, and where E, B are arbitrary constants, all right, and y1 and y2 can be independent or sometimes dependent. Anything, it can happen. Okay, so these are the common things before going to the power series method. Now, how to do this power series solution? So, the procedure. So how to do this is that number one, let y is equal to a naught plus a1x plus a2x square plus so on up to say a cube x to the power k. That means I'm writing y as a summation from a is equal to 0 to some infinity a k continued. Okay, so x to the power k. This is what we assume first. This is, let us say that this happens. Okay, we will assume that y is equal to this. Okay, now once we have assumed that, what will be the dy dx? Because ultimately our aim will be, once we assume certain solution, we have to put it in the differential equation, right? So for that, we might have a differential equation which has the first order derivative of y. So what it will be? It will be, if you look at the series, this will be 0, a naught will be 0. So it will be a1 plus 2 a2x and so on. Means there will be so many things, right? So I can write in terms of summation this dy dx as k is equal to, it will start from 1 now to infinity, k ak x to the power k minus 1, right? Then only if you put k is equal to 1 here, this becomes x to the power 0. Right? This is what we can do. You cannot put 0 here because it will be x to the power minus 1, which is not possible. Third, that is dy by dx 2. What it will be here? So some 2a2 plus 6a3x and so on. It will continue. So can we write it in terms of summation? Yes, we can. This will be nothing but k is equal to 2 to infinity, and there will be a double differentiation. Okay, so at x to the power k minus 2. So again, we can see that below 2 you cannot write, because if you write there, it becomes 1 upon x, 1 upon x squared, which is not the way we have represented the y. Done. Once we have done this, we have to, so we now have to put whatever we have got for y, the first order derivative of y and the second order derivative of y in the actual OT, right? So this is what you have to do. Now you have so many coefficients like a k, that means a naught, a1, a2. There are so many coefficients, right? So what we will have to do for those coefficients, the coefficients, or I would rather say, let me define first. So a naught, a1, a2, and so on. There will be many, right? Coefficients of various power of x, various power of x has to be equated to some zero. So I will come to it when I will explain it. You will understand this. Next is substitute the values of a naught, a1, and so on. There's so many coefficients which is there in the ordinary differential equation to get the series. So of course it will be getting clear when we solve some questions, and we will solve some about 2 3 questions about the power series method, how to apply it. So that is what we are going to do now. Once we have done this, then we will come to the Corbinius method, the last part of our so-called this course. Okay, so and we will finish the lecture. Okay, so let's go to the question. Fine. So that will give you the demonstration about the processes which is to be seen. Okay, so the question is 1 minus x square y double dash minus 2x y dash plus 2y is equal to 0. Suppose this is what you have. Okay, so now what we will do is that let's just check, right? 1 minus x square is not equal to 0, definitely when x is equal to 0. So we can say that x is an ordinary point. Okay, just a minute. Right? It is some kind of an ordinary point. Now, Let us assume, as we have told you, the first step is let us assume that y is equal to summation k is equal to 0 to infinity a k x to the power k. Fine. So what will be the dy dx? Because we have to calculate everything. So it will be is equal to 1 to infinity a k x to the power k minus 1. Just differentiate x with respect to x once. Now differentiating it twice. So it will be k is equal to 2 to infinity a k into k minus 1 x to the power k minus 2. Right? So y dy and d2y by dx2, this we have already found out. Great. Now we have to put it into the main equations, right? So what is the main equation? 1 minus x square y double dash minus 2xy dash plus 2y. So let's put it. So what it will be? Let me write it. So it will be 1 minus x square, the double derivative, right? So it will be k is equal to 2 to infinity a k minus 1 x to the power k minus 2. This is the first term of the ordinary differential equation. Great. Second term minus 2x summation k is equal to 1 to infinity because it's the first derivative k x to the power k minus 1. Done. And the last term 2 times the y. So it will be ak x to the power k, which is equal to 0. It's all are homogeneous equation as I have told you. So this is what you solve it further. So how will I do it? So this is suppose here. So it is k is equal to 2 to infinity. So it will be ak k minus 1 x to the power k minus 2 plus or minus k is equal to 0 to infinity. We'll understand why I am doing it. ak k minus 1 x to the power k. How? No, I am now multiplying this x square with this. So it will be x k minus 2 plus 2, which is k. Right? And once we have written is k, the summation will change here. Fine. Next, minus 2, this term we are writing. So k is equal to 0 to infinity because there is an x which will get multiplied with x to the power k minus 1 to get x to the power k. So ak k x to the power k. Right? And finally, 2 times the original one, whatever is there, is equal to 0 to infinity, ak x to the power k, which is equal to 0. So this is the, after solving, we are getting this. Further, we can reduce this to something like this. The first term we will not touch upon much. So a k minus 1 x to the power k minus 2 minus all terms are in the summation k is equal to 0 to infinity, that we will be writing. So here what will happen is that, can we write this as, okay, let us first write it like k minus 1. See, already there is a negative sign, so I am writing k minus 1 plus 2k because there is a negative sign here and minus 2. This ak x to the power k, and this should be equal to 0. Right? We can write this further writing k is equal to 2 to infinity ak k minus 1 x to the power k minus 2 minus, again writing the summation k is equal to 0 to infinity, and we solve inside and write whatever is there. So k square minus k plus 2k minus 2, and you have ak x to the power k. This should be equal to 0. Further, in the next step, k is equal to 2 to infinity. See, the first term we are not touching upon. Let it be like this, minus the summation which is there, k is equal to 0 to infinity. And what about this? K square plus k minus 2. Done. ak x to the power k, this should be equal to 0. Mostly things are done. Next step is that we have to equate coefficient of x to the power k equal to 0. Okay, coefficient of x to the power k should be equal to 0. So this is what actually I am trying to write here. So the coefficients have to be equated to 0. Actually it's various power or x to the power k which is mentioned. Okay, so that is what I am trying to tell there. Okay, so equate coefficient of x to the power k equal to 0. So one, we can see that here x to the power k is there, but here we don't have x to the power k. But can we convert? Yes, we can. So how to do this? How to convert x to the power k minus 2 to x to the power k? Just by writing k tending to k plus 2. Right? If I put k is equal to k plus 2 here, then what will happen? It will be x to the power k. So the summation will also going to change. K is equal to k plus 2 now. Right? So what will happen is that finally your summation will be, now k is equal to 0 to infinity. It will be a k plus 2. Now k will be k plus 2. So it will be k plus 2. Next, k minus 1. So it will be, I will write it in exactly k plus 2 minus 1, x to the power k plus 2 minus 2. Done. Plus the second will be as it is because it is already in terms of x to the power k. So ak, what was the thing? K square plus k minus 2 x to the power k. Put that equal to 0. So now further we can write this k is equal to 0 to infinity a k plus 2. This is k plus 2 and this is k plus 1. All right, x to the power k is there plus the same summation now k is equal to 0 to infinity a k, and you have k square plus k minus 2. You can reduce it. You can do some kind of middle term factoring or something, but it's not required also. Fine, this is equal to 0. Now, what I have told you that equate the coefficients of x to the power k coefficients that is equal to 0. Leave the summation. So, what we will write is that a k plus 2 k plus 2, k plus 1. This is the coefficient from the first term plus coefficient from the second term. That should be equal to 0. All right. This is the next step. So I put ak plus 2 only in the left hand side and all other terms I just put it in the right hand side. I'm sorry, there is a negative sign. Sorry. Right? There is a negative sign. So it will be plus. This will be ak divided by k plus 1, k plus 2. Right? So what we have found out finally is an expression which relates the ak plus 2 and ak in terms of k, the k values, right? The powers. Fine. So now if you want, you can reduce this. How will you do it? Simple. It is just k square. Uh, so just try this minus 1 plus minus root over e square uh, plus 4 to the 8 divided by 2, right? So k will be minus 1 plus minus 3 by 2. So 1 will be 3 minus 1 by 2, which is 2. Sorry, 1. And another will be minus 3 minus 1, which is minus 4 by 2, which is minus 2. So the above term will be therefore k minus 1 and k plus 2. Okay. So let me write clearly. This can be written as this. So finally, another way we can write k plus 2 is k minus 1, k plus 2, ak divided by, in the denominator we have k plus 1, k plus 2. So you can see that k plus 2, k plus 2 cancels. Again, we can write ak plus 2 is equal to k minus 1, ak divided by k plus 1. We have reduced the recurrence relation. Why it is called the recurrence relation? Because every time you change the value of k, you will get the coefficients. Alright, so this is what we have got. Fine. Let's put k is equal to 0 initially to start with. So k is equal to 0 will do what? A2, which is equal to 0 minus 1, which is minus 1, 0 plus 1, which is 1, and this is A naught. Right? So A2 will be equal to minus A naught. Perfect. This we can do. Next. K is equal to 1. So it will be 2 plus 1, 3. This will be 1 minus 1, 0. Right? So A3 will be 0. K is equal to 2. So it will be A4. 2 minus 1, 1. 2 plus 1, 3. And this will be A2. K is equal to 3. That is A5, which is equal to 3 minus 1, which is 2. 3 plus 1, which is 4. And A of 3. A of 3 is already 0, so it is 0. Okay, so let us do some more. So K is equal to 4. So what will happen? So it will be A6, which will be 4 minus 1, which is 3. 4 plus 1, which is 5. Okay, and A4. And A4 is already 1 by 3 A2. And 1 by 3 A2 is minus A naught. So let us write this, right? So 1 by 3 A2 can be written as minus 1 by 3 A naught. Then what about this 3 by 5 A4 can be written as 3 by 5 into minus 1 by 3 A naught. This be cancels, so it becomes minus A naught by 5. So on, it will continue. Okay, then how will we write the solution therefore? So the solution becomes y is equal to A naught, which is some non-zero constant. We don't know what it is, but right now it is a non-zero constant, plus A1 times x. Where is A1? So you cannot, I think, find the A1 here, but wait just a minute. So if I put here k is equal to 1, which is 2 plus 1 is 3, yes, see, this part is 0, right? For this k is equal to 1, this part is 0, times some A1 is always there. So I am putting that A1 is not equal to 0. Okay, it is an assumption, and it is a true assumption because already this part is 0. This part might not be 0. It's not required to be 0. So we can have this a1 times x minus a naught x square 1 because k is equal to 2 corresponds to this. All right, is it fine? I think this will be a naught by 3 in some sense, right? No, okay, I'm sorry. Wait, I'm doing it in a wrong way. So y is equal to, this is a naught definitely, plus a1x because a1 is not equal to 0, I have shown. What about a2? A2 is minus a naught, right? So it will be minus a naught x square. What about a3 is 0. Next a4 is minus 1 by 3 a naught x 4 because x cube is here. Now it is x4. Similarly a5 is 0. What about a6? This. So minus k naught by 5 x to the power 6, right? And so on. Don't need to write everything. So what it will be, therefore, y is equal to a naught, I can take common, 1 minus x square minus x4 by 3 minus x6 by 5 and so on. Plus the second solution is a1x. That's all. Okay. Why am I getting A1? Because at A is equal to 1, you have a valid A1 here. But 1 minus 1 becomes 0 here. So this part before A of K is 0. So A1 might not be 0. That's why I'm assuming A1 is not equal to 0. Fine, and hence we can write this. Okay, so this is the solution, or this is the answer for the above question which we have seen. Okay, but this is a time-taking question. But once you start practicing it, it will not take much time. So I will show two more examples, which is somewhat complicated. We will do that, and then we will move towards the Frobenius method. Okay, so let me see where the questions are, and then we can solve. Fine, let's go ahead with another question. Okay. So again, using the power series method, you just have to solve this particular question d2y by dx2 plus x square y, which is equal to 0. Okay, so it's not complicated, it looks complicated, but it will be easy now. So first step, assume y is equal to some power series solution. K is equal to 0 to infinity, ek x to the power k. What about we have only d2y dx2? So directly you jump to the second order derivative of the y. So it will be k is equal to 2 to infinity, definitely, k minus 1, k x to the power k minus 2. Right? Directly we are jumping to the second order derivative. Fine. Once we have this, put it in the ordinary equation. So what will we get? This k is equal to 2 to infinity, k minus 1, ak x to the power k minus 2. What about this? Some x square summation k is equal to 0 to infinity, and ak x to the power k, which is equal to 0. Fine. So now what we can do is that we have to reduce. So we have to reduce to x to the power k. So in this case, the first term k can be rewritten as k plus 2. But in this term, because this 2 will be multiplied with this, so k can tend to k minus 2. So therefore, we have k is equal to 0 to infinity, k plus 2, k plus 2 minus 1, a k plus 2, x to the power k plus 2 minus 2, plus summation, again k is equal to 0 to infinity, a k minus 2, x to the power k minus 2 plus 2. This should be equal to 0. So 2 cancels, 2 cancels. So you get summation. I'm not writing k is equal to 0 to infinity, it is understood now. So k plus 2 into k plus 1, a k plus 2, x to the power k, plus summation a k minus 2, x to the power k, which is equal to 0. Equate, equate the coefficient of x to the power k to 0. So what will you get? K plus 2, k plus 1, ak plus 2, plus ak minus 2 is equal to 0. Right? So on the left hand side, put the ak plus 2. On the right hand side, it will be ak minus 2 divided by k plus 1 and k plus 2. Alright? So this is what is the recurrence relation which we are getting. Fine. Can we put here k is equal to 0? If you put here k is equal to 0 on the right hand side, you will be getting 0 minus 2, which is a minus 2, which does not exist. Okay, which does not exist. And for k is equal to 0, a2, and the right hand side it does not exist, right? So RHS will be something like a minus 2, which we assume to be 0. All negative coefficients we will assume to be 0. Fine. K is equal to 1, A3, put it here, K is equal to 1. So 1 minus 2 will be minus 1. So minus A minus 1, which is also 0. So all negative coefficients, put that equal to 0. So A3 will be 0, A2 will be 0. Great. Come to K is equal to 2 now. So it will be A4, and here it will be minus A0, right? And it will be 2 plus 1, 3, 2 plus 2, 4. Alright, this is the first value which we are getting. And hence we can write A0 is not equal to 0. Although A2 is 0, A3 is 0, A0 is not equal to 0. K is equal to 3. A5, which is minus A1 divided by 3 plus 1, 4, 3 plus 2, 5. So this becomes A1 is also not equal to 0. K is equal to 4. A6 here minus A4. Already whatever the value is, this is 0. I'm sorry, just a minute. 4 minus 2 is 2. This is 0. A2 is already we have found out to be 0. K is equal to 5, A7. So it will be minus A5 minus 2, which is 3. So whatever in the denominator, you don't need to calculate. A3 is already 0, so put that equal to 0. K is equal to 6. Let's do it further. 8, which is nothing but A4 divided by. Now, 6 plus 1, 7. 6 plus 2, 8. Okay. So 7 times 8. Remember, this is dot. And what is A4? Is minus A0. So it will be A0 divided by 8 times 7 times 4 times 3. And so on. You can write. Okay. Not too many you have to write. Just some values if you can calculate, that will be easy. So at least you go to K is equal to 6. Otherwise, difficult for you. So how will the solution look like? So A0 plus A1x, definitely, because A0 and A1 are not equal to 0, minus. Because if it is equal to 0, then everything is 0. That does not have any meaning. Okay. So this is 1. Next is A0. So A2 is 0, right? So A2 is 0. 0 times x square minus 0 times x4, or plus you can write here. Doesn't x cube. Now the next one is plus A3. I'm sorry, A1, A2, A3, A4, right? A4 x4 and so on, right? This is the thing. So y is equal to A0 plus A1x. These are all 0. Now what is A4? Is minus A0 by 12 x to the power 4. Okay. Minus A1 by 20 x to the power 5. Then A6, A7 all are 0. Then you have A0 divided by 12 into 7 into 8 x to the power 8 and so on. So y can be written as therefore A0 1 minus x4 by 12 plus 1 upon 12 into 7 into 8 x to the power 8 and so on, plus A1 times x minus 1 by 20 x to the power 5 and so on. So there are two solutions of our series which you can clearly see because it is a second order differential equation. So you will have two different series and we are getting that. Okay, so this is how you have to proceed. Fine, we will do another question and then we will go towards the Frobenius method. Okay, which is a similar kind of thing like power series only. This is also a power series, but it's a different sets of rules and things. Okay, and remember this Frobenius method which we will be talking about. Its application is different types of polynomials can be generated, like Legendre polynomials, Laguerre polynomials, then Hermite polynomials, and Bessel's polynomials. So all these polynomials can be found out using Frobenius method. I will not go into details of how you will find out because it's a long task. So you can try practicing, but I would say that Hermite polynomials are useful in the quantum mechanics in physics, particularly quantum harmonic oscillator. So you know that E is equal to n plus half the h cut omega. So there you might require for the wave functions you might require the Hermite polynomials. So it's good to look into that, and it is already mentioned, I think, in the week 8 note. So I will cover only the mathematical part, not the Hermite polynomial, but at least give you an idea through the Frobenius method how to solve all these different polynomial based equations. Okay, so let us do one more question on this power series, and then we will move to Frobenius method and solve two examples, and then we will stop. Okay, so the next question is again using power series method to solve for this d2y by dx2 plus xy equal to 0. So again, you can see that second order derivative jump. So the first step is this y is equal to ak x to the power k, and you need the second order derivative. So directly go to that. So it will be summation k minus 1 ak x to the power k minus 2. Right? And of course, the summation will be from 2 to infinity. This will become k is equal to 0 to infinity. Put this in the main equation. So you will get k is equal to 2 to infinity, k minus 1, ak x to the power k minus 2 plus. So x times this, so x times k is equal to 0 to infinity, ak x to the power k which is equal to 0. So again, writing this, k is equal to 2 to infinity, k minus 1, ak x to the power k minus 2 plus this summation k goes to now let us not write it right now. This will be k equal to minus 1. So let's write this now k plus 1 equal to 0, because ultimately you have to reduce it to the x to the power k. So how will you reduce it? K will tend to k plus 2 here. Here it will be k minus 1. All right, just do that. And you will know that the summation will be k is equal to 0 to infinity in both the ends. So it will be k plus 2, k plus 1, and just directly writing, you know now how to do it. So a k plus 2, x to the power k, plus the summation will be the same now, k is equal to 0 to infinity, a k minus 1, x to the power k equal to 0. Done. This is done. Now equate the coefficient of x to the power k equal 0. So k plus 2, k plus 1, ak plus 2 plus ak minus 1, that should be equal to 0. So ak plus 2 you leave it in the left hand side, ak minus 1 you keep it on the right hand side, and divide by k plus 2, k plus 1. This should be the recurrence relation formula. Now you generate the a0, a1, a2, whatever you wanted to. So let's put k is equal to 0 first. So if put k is equal to 0, it will be a2. This is minus a minus 1, which is equal to 0. We will assume k is equal to 1, a3. 3 minus 1, I'm sorry, 1 minus 1 is 0. This can be fine. So a0 is not equal to 0 for sure. Otherwise, entire solution will be 0. So it's not feasible. Okay, then 1 plus 1 is 2. So it will be like this. So it will be minus a0 by 6. Then k is equal to 2. So it will be a4, which is equal to minus a, 2 minus 1, which is 1. So a1 is also not equal to 0. And you have 2 plus 2, 4, 2 plus 1, 3. Right? So it will be minus a1 by 12. Okay, next k is equal to 3, which is a5. Let's see what happens. So it will be definitely minus a2. So whatever it is, a2 is 0, so it will be 0. K is equal to 4, a6 minus a4 minus 1, which is 3, divided by 4 plus 2, 6, 4 plus 1, 5. So 6 into 5. So it will be minus A3 by 30. Now what is A3? A naught by 6, right? Minus A naught by 3. So it will be A naught divided by 6 into 30. Done. A is equal to 5. Will be A7, which is minus A4 divided by, I think, 7 into 6. So it will be minus A4 by 42. And A4 is minus A1 by 12. So it will be A1 by 42 into 12. Similarly, now K is equal to 6, A8, which is nothing but minus A5, which is 0. A5 divided by something will be there, definitely. K is equal to 7. I have told you that go up to K is equal to 7 or K is equal to 8, it will be better. So A9 is also not required, but let's calculate this one and end it. Okay, so it will be 9 minus, oh, sorry, 7 minus 1, that is 8. Minus A8. I don't think this will be something wrong. So K is equal to 7, right? So it will be 6. So A6 divided by 7 plus 1, which is 8, 7 minus 1, which is 6. Okay. 8 and 9, sorry. So 8 into 9. So minus A6 divided. So you can reduce it. It doesn't matter. There's so many things. So finally, how will I write A naught plus A1x plus A2x square? First write it. A3x cube, A4x4, and so on. Okay. Now you write actual one. So A naught, A1x is there, so A1 is fine. What about A2? A2 is 0, correct? So A2 is 0, leave it. A3 is minus A naught by 6. So it will be minus A naught by 6, but it will be x cube. Okay, next A4 is minus A1 by 12 x4. What about A5? 0. What about A6? Minus A3 by 30. So A3 can be written A naught by 6 into 30. So plus A naught by 30 into 6, x to the power 6. And so on, let us say. Okay, so why? You know now what I have to do. A naught has to be taken common in one case. So 1 by 6 x cube plus 1 upon 30 into 6, x to the power 6, and so on. Okay, this is one set. Second set is A1 x minus 1 by 12 x to the power 4, and so on. You can write many other terms, but it's your choice. Okay, so this is the answer. This is how you have to solve the power series solution through the power series method. OD using power series method. Okay, now let's go to the Frobenius method, an important method to solve any, as I have mentioned, the polynomial equations. I will write it down once I finish it. So this is a somewhat bigger approach, so it will take some time. Okay, so we will see this. Okay, so let's go ahead with a new way of doing the exercise of solving the ordinary differential equation when you have some kind of a polynomial in a homogeneous equation. Okay, that is Frobenius method. But it's a very lengthy method, definitely. So if x is equal to 0 is a regular singular point. Remember, this is the singular point. That means it should vanish. And you have an ordinary differential equation y double dash plus p1x y dash plus p2x y is equal to 0. Okay. In that case, you have to say that y is equal to x to the power m. See, it is written completely in a different way. X to the power m a naught plus a1x plus so on up to whatever, so it go to infinity. So instead of writing e is equal to 0 to infinity a k x to the power k, now it is k plus m. Remember this. Now, what we have to do is that put this y in equation and find m. And there is a way to find m. You will see that. And there are some methods like when m1 and m2 are, see, there will be two solutions, right? Because it's a second order equation. So it will be having two real and distinct roots. So it will be m1 minus m2, which is not equal to 0. This is what it means. So we will have to write y is equal to some c1 y of m1 plus c2 y of m2. You will never understand like this. You have to go for some question to understand what we are trying to say. So when m1, m2 are real but equal, you will mostly get this kind of a thing. So m1 is equal to m2. All other conditions are not required to be discussed right now. So c1 y of m1 plus c2, we have to do delta y by delta m. Similar things which we have done earlier also for ODE solving. Same thing. So okay, this will be in one because the roots are same. Okay, there are other steps also. I am skipping those. Okay, let's directly jump into the question and see how it can be done. Okay. So let's go for a question. Let us say using Frobenius method, you have to solve this equation x minus 1 y double dash plus 3x minus 1 y dash plus y equal to 0. This is suppose the first question which we will be talking about. Okay. First thing you have to check whether x is equal to 0 is a singular point or not. Put this x into x minus 1. Okay. If x is equal to 0, then x6 minus 1 is 0. Right? Therefore, x is equal to 0 is a regular singular point. This is proved. The first thing you have to check this. Okay. Now, once you have checked this, go ahead with the assumption that y is equal to k is equal to 0 to infinity. Instead of writing a k x to the power k, I will write k plus 1. Then dy dx, very similar to that, k is equal to 0 to infinity a k. Now it will be m plus k x to the power m plus k minus 1. Look, I have kept the k same. I am changing the m. This is what is the new thing. Whatever the power which we were doing it in the power series solution, we have to change this, right? The t is equal to 1 to infinity, t is equal to 2 to infinity, the double derivative. Here we are not changing the solution because we are saying that whatever the minus 1 which is coming, it is with the m. Okay. Hence, we don't need to change it. So d2y by dx2, again, it will be k is equal to 0 to infinity ak m plus k, m plus k minus 1. See, again, we are not able to change m plus k minus 1. That's all. K you don't need to do. Now, so next step, of course, whenever you have calculated everything, put this in the ordinary differential equation. Great. This is done. So what we have to do next? Just solve. Okay. So the first is the summation. Since all the summations are same, that is k is equal to 0 to infinity, we don't need to think about it. Okay. So we don't need to think about this. So you have this particular equation, and this is how we are proceeding. So you have x into x minus 1 ak m plus k into m plus k minus 1 x to the power m plus k minus 2. So what I am doing for the Frobenius method, first step is you check whether the differential equation is having x is equal to 0, a regular singular point or not. So for that, check the highest order of the differential equation, highest order term of the differential equation, and check its coefficient. Put x is equal to 0 in there and see whether this function is equal to 0 or not. Yes, it is 0. So x is equal to 0 is the regular singular point. Once we have proved this, we can proceed for the Frobenius method. So in the Frobenius method, unlike the power series method, where we were writing k is equal to 0 to infinity ak x to the power k, now we are writing k plus n. Okay. Why we are writing? You will understand. When we differentiate it once, it comes out to be ak m plus k x to the power m plus k minus 1. So, so that the power is now, you don't need to change the summation. So it will automatically be coming there. Okay, so now we just put it into the equation and try to solve it. Next, the next term is 3x minus 1 summation. It is a long term summation, I am telling you. So ak m plus k x to the power m plus k minus 1, this first order differentiation. And the last term, that is ak x to the power m plus k, that is equal to 0. Right? This is what you have. Excellent. So let's go ahead for the next step. So first is multiplication of x square, definitely. So if you are, so this is see x square minus x, right? So first x square I am multiplying. So it will be ak m plus k m plus k minus 1 x to the power m plus k minus 2 plus 2, right? This x square minus, again I am writing a summation ak, same thing, m plus k m plus k minus 1, but this time it is x m plus k minus 2 plus 1, right? Okay. Next is 3x. So 3 times summation ak m plus k x to the power m plus k minus 1 plus 1. And finally minus, so it is 3x minus 1. So this m plus k, whatever is there, x to the power m plus k minus 1. And the last term ak x to the power m plus k, that's all, equal to 0. Okay, so we have completely taken term by term and written it here. So now what we can write further from this is that ak, now you have to combine all those terms. So this, look at this, 2 cancels out, this becomes minus 1, this 1 cancels out to m plus k. So there are two terms, x to the power m plus k minus 1 here and here, and all other m plus k. So try to write m plus k first. So first is ak m plus k m plus k minus 1 plus 3m plus k, and finally plus 1. This to the power x to the power m plus k minus summation ak m plus k m plus k minus 1 plus m plus k x to the power m plus k minus 1. This should be equal to 2. All right. This, sorry, this one, this and this. And all have a negative sign, so I have taken negative sign common. Next step, what we will do is that we try to find lowest power of x, which is nothing but x to the power m minus 1 for k is equal to 0. So look for x to the power m minus 1 for k is equal to 0. And we can see this term has that ability to do. Here we cannot. It is x to the power n. So in the second term, if k is equal to 0, we can have x to the power m minus 1. So now equate the coefficients of lower order, that is x to the power m minus 1 equal to 0. So what we will do is that you have your m plus k into m plus k minus 1 plus m plus k is equal to 0. So m plus k can be taken common, m plus k minus 1 plus 1, which is equal to 0. So it will be m plus k whole square, which is equal to 0. Now k is already 0, so m square will be equal to 0. So m will be 0 and 0. So there are two solutions, m will be 0 and 0. And we know for n is equal to 0 is equal to 0. So two real but equal roots. And for that solution we do. But we will not consider the solution right now. Let us calculate the power series first. Okay. Once this is done, okay. So now fine. This is what we have seen. And altogether, if you look at, so it will be like this, right? A naught because k is equal to 0. Okay, so AK you can write for the time being. Okay, so it will be A naught. So A square will be 0. So I am writing that A naught is not equal to 0. Fine. This is important. Next step is look for next higher order, next order or next higher order power of x, right? Which is nothing but x to the power m. X to the power m is possible. So first term, put k is equal to 0. Second term, put k is equal to 1. Right? So let's do it. So putting the first term a is equal to 0 becomes a naught m minus 1 plus 3m plus 1, and the second term it is minus a1 m plus 1 whole square equal to 0. Okay, and equate, so coefficient of x to the power m equal to 0. So these are the steps, and we do that. Based on that, we are we can say that to solve this, we get something like this: minus a1 m plus 1 whole square equal to 0. And for m is equal to 0, you get a naught is equal to a1. Great. This is an interesting result. Next, now we will generalize. Just like we have generalized it for the power series, Here also we will generalize. So what we will do is that generalizing means equating the coefficient of x to the power n plus k to 0 to get a recurrence relation. Okay, so let's try that. So how will we do it? X to the power m plus k, right? So you have the original equation that we have written this. Yes, this one. This is m plus k minus 1. This is m plus k. So in this case, we can write it as it is thing, but in this case, we have to do k tend to k plus 1. So I am writing it this again, and you will understand. So our final expression was that you have a summation ak m plus k m plus k minus 1 3 times m plus k plus 1 x to the power m plus k minus summation ek m plus k m plus k or square, right? This x to the power m plus sorry, x to the power m plus k minus 1. Okay, so this should be equal to 0. So for the first term, as it is, second term, k needs to be now k plus 1. Now put it in the main equation and put it. So it will be ak m plus k. I have already solved this. So m plus k plus 2 plus 1 minus k plus 1 because this has to be now like this, and m plus k plus 1 whole square, that is equal to 0. So my if you solve it further, you will see that this will be m square plus mk plus 2m plus km plus k square plus 2k plus 1. Solve this, you will get this minus ak plus 1 m plus k plus 1 whole square equal to 0. What you can do here, ak, so it will be now m square plus 2mk plus 2m plus k plus 1 whole square minus ak plus 1 k plus m plus 1 whole square equal to 0. Further, ak, I can write now this k plus m plus 1 whole square is equal to ak plus 1 k plus m plus 1 whole square. So what you get finally? Ak plus 1 is equal to ak. Very interesting to understand. Correct? So now what we can write is that the original solution y will be x to the power m a naught plus a1x plus a2x square and so on. Right? So we will be writing like this: y is equal to a naught x to the power m 1, because a1 is nothing but a naught. You can see it from here. So it will be 1 plus x square and so on. So this is one of the solution y1. What about the second solution? It will be delta y1 by delta m. So what it will be? With respect to m, it is differentiated. So it will be a naught x to the power m log x into the same thing, 1 plus x square and so on. Okay, so final solution will be y. Okay, now just a minute. So y1 has to be at m is equal to 0 because we have found out there are two solutions there. So we found out m is equal to 0 is the solution, is the root. So y1 of m is equal to 0 will be a naught 1 plus x square plus x cube, whatever. And y2 at m is equal to 0 is a naught log x 1 plus x square and so on. Hence, the solution becomes y is equal to some a times 1 plus x square plus x cube and so on plus b log x, say 1 plus x square plus x cube and so on. This is the answer. So you can see that step by step if you go, it's a very, very lengthy process, but this is the way you can go ahead for, so the applications part, if I just write. So application of Frobenius method is that you can solve Legendre polynomial equation, polynomial differential equation, right? Then Hermite differential equation, third uh, Bessel's Bessel's function. So all their solutions, that is, what will be the solution for the first? Like the Legendre polynomial, Hermite polynomial, Bessel's polynomial. Okay, this can be found out using Frobenius method. It's a lengthy process, and all this has a role to play in, particularly in quantum mechanics. Okay, so this is an interesting part. Okay, so this is done. Let me give you another set of differential equation and let's finish after that. Okay, so we have about 20 minutes, so we can solve one another question and finish it. So another example of Frobenius method is this. Let's say you have 3x d2 y by dx2 plus 2 dy by dx plus y equal to 0. So check for the regular singular point whether x is equal to 0 is it or not. So you have 3x. So put x is equal to 0. So 3 into 0 is 0. Therefore, x is equal to 0 is a regular singular point. That means the Frobenius method can be applied. First assumption, y summation k is equal to 0 to infinity ak x to the power k plus instead of x to the power k. Dy dx required. So the same summation k is equal to 0 to infinity ak k plus n x to the power k plus n minus d2y by dx2 is k is equal to 0 to infinity ak k plus n k plus n minus 1 x to the power k plus n minus 2. Done. So now put this in the actual ODE. So I'm writing now. So it will be 3x. There is a summation 2k, k plus n, k plus minus 1, x to the power k plus n minus 2 plus 2. Somewhat easy equation this time. K k, k plus n, x to the power k plus n minus 1. Finally, k k, x to the power k plus n. Equal to 3. Next, further you have to solve it, right? You have to solve it. The summation 3 you can keep it outside. K k, k plus n, k plus n minus 1, x to the power k plus n minus 1 because one x is multiplied. Here there is nothing, so it will keep as it is. And finally, done. Now what? Check for lowest power, or lowest order of x. So it will be x to the power n. So we find for m minus 1 for k is equal to 0. Okay, so this can be done here. So first two terms possible. Second time it's not possible. So first two term you write. So it will be now 3 m m minus 1 plus 2m is equal to 0. How am I getting it? 3 k is 0, so m k is 0 m minus 1 and 2 times m, that is equal to 0. Right? So 3m squared minus 3m plus 2m is equal to 0. 3m squared minus m, which is equal to 0. M can be taken common. 3m minus 1, which is equal to 0. So m is either 0 or m is equal to 1 by 3. So we can clearly see m1 is equal to 0, m2 is equal to 1 by 3, real and distinct. Done. Now we look for coefficient of next higher order term. Higher order term, which is x to the power m over k is equal to 1. Oh, sorry, x is equal to x to the power n. So for first term, k has to be equal to 1. But for the first and second term, and for the third term, it should be k is equal to 0. All right, then only we can get. So once we do that, we get 3m plus 1, m plus 1 minus 1 plus 2m plus 1 times ak, so a1 plus a0, which is equal to 0. So for m is equal to 0, you get 2a1 plus a0 is equal to 0. So a1 is minus a0 by 2. And for m is equal to 1 by 3, it will be 3 into 1 by 3 into 4 by 3 plus 2 into 4 by 3 into a1 plus a0 equal to 0. This gives you a1 is equal to minus 1 by 4. And you will see that when we find out the general recurrence relation, you will be getting the same thing. Now, for generalized recurrence relation, equate the coefficient of x to the power n plus k equals 0. So once we do that, we get 3ak plus 1, k plus m plus 1, k plus m plus 2ak plus 1, k plus m plus 1 plus ak, which is equal to 0. So after solving everything, you can reduce this to ak plus 1 minus ak divided by k plus m plus 1, 3k plus 3m plus 2. Alright, so this we can find. Now, what we will do is that there are two sets of solution. So let's do it for n is equal to 0. So ak plus 1 for n is equal to 0 becomes minus ak, and you can see it is k plus 1 and is 3m plus 2. I'm sorry, 3k plus 2. Right? Now for m is equal to 0, let's say for k is equal to 0, what we will get? A1 is equal to minus A0, 1 times 2. So it will be minus A0 by 2. Exactly what we have got. K is equal to 1, A2 minus A1, 1 plus 1, 2, 3 plus 2, 5. So it is minus A1 by 10. Right? And what about A1 is minus A0 by 2, so A0 by 20. Similarly, K is equal to 2. Just end it here. So it is minus A2 divided by 2 plus 1, 3. 3 2 is 6 plus 2, 8. It is minus A2 by 24 or minus A0 by 24 into 20 and so on. Let's go for m is equal to 1 by 3. So what is the reconciliation for that? Ak plus 1 is minus ak. You get k plus m plus 1, right? So it will be 1 by 3 plus 1, which is 4 by 3, and 3k plus 3. Put k is equal to 0. We get a1 is equal to minus a0. So 0. So it will be 4 by 3 into 3. So minus a0 by 4. Let me show that we have got that also. Right? K is equal to 1. A2, which is equal to minus a1. That will give you 7 by 3 into 6, which is minus a1 by 14. So it will be a0 by 14 into 4. Similarly, k is equal to 2 is a3. So minus a2 divided by 10 by 3 into 9. So 3 by 9. So it will be minus a2 by 30. And that will be a0 divided minus a0 divided by 30 into 14 into 4. Okay. So how will we write the actual solution? Y is equal to what? X to the power m a0 plus a1x plus a2x square and so on. Right? So y1 will be for n is equal to 0. So y1 will be equal to a0 1 minus x by 2 plus x square by 20 and so on. Let me not write further. And m is equal to 1 by 3, that is y2, which will be a0 x to the power 1 by 3. Right? Why? Because you have x to the power m outside. So it will be 1 minus 1 by 4x plus 1 by 56 x square and so on, whatever it is. So the net will be some a times 1 minus x by 2 plus x square by 20 and so on plus b into x to the power 1 by 3 1 minus x by 4 plus x square by 56 and so on. So this is the solution. Okay, so with this, I think we can end today's lecture. So we have seen from the beginning, I will just repeat once. So in the starting of the course, we have started with the vectors. We have gone through in details the linear algebra part of the vectors, and we went to the matrix, eigenvalues, eigenvectors, how to find it out. We have seen some operators, how it is useful in the quantum mechanics. We have also discussed that. Then we went towards the Fourier transform, Fourier series and Fourier transform using the Dirichlet condition, Fourier series, any periodic function and certain conditions have to be satisfied to be written in terms of known functions like sine and cosine if the function is periodic. Once we do that, we deduce the Fourier transform part. We have seen the Fourier transform as well as the inverse Fourier transform. Then we went to Laplace transform. Okay. In between that, we started the ordinary differential equation. We have seen how to solve the basic your first order differential equations, then second order differential equation with homogeneous equations and inhomogeneous equations. Homogeneous equation needs to be solved using auxiliary equations, and it will just have the complementary solution. Once you go to inhomogeneous, where the forcing function will come, you have to solve for the particular integral or particular solution. There are several steps to do the particular solution for the ODEs. We have discussed that set of rules based on different forcing functions, whether it is exponential, sine, cosine, x to the power n, whatever. Okay. So for inhomogeneous equation, we have both complementary as well as partial particular solution. Next, we use Laplace transform and inverse Laplace transform to solve for the ordinary differential equation. This is another way. We have used the superposition principle, that is writing in terms of some coefficients and find out the values of the coefficients for the particular solution. That is another way we have seen how to find out the particular solution. After that, we went to the Green's function. Using Green's function, we have solved the ordinary differential equation and particularly the particular function. Finally, today we have looked at the power series method and in fact the Frobenius method. So let's see what we have done today. We have started with a question on finding out the particular solution using the Green's function. This is an interesting question, and this is a simple way to solve the particular solution using the Green's function. And then we went towards the power series solution. And the easiest part of the power series solution we have discussed about the regular point and singular point. Singular point becomes important for the Frobenius method. We have seen there is a condition that x is equal to 0 must be a regular singular point. This is the first part before proceeding for the Frobenius method. But for the power series method, we generally write this any y in terms of x as this kind of a power series. We differentiate it once and twice, and in that way, the summation will change. Put it into the main equation, look for the x to the power k term and equate its coefficient to 0 and change the summation in such a way. Okay, so equate the coefficient of x to the power k to the 0. Once we do that, we get some kind of a reference relation in terms of k, and from there we derive certain coefficients, and finally we write that as the final solution. Of course, you will have if there are two series and we are getting it each and every question. Okay, so these are the three questions which we have seen for the power series solution. Then we went towards the Frobenius method. For the Frobenius method, this is an important condition that x is equal to 0 should be the regular singular point. And instead of writing y as a direct power series like ak x to the power k, we are writing it as x to the power m times the ak x to the power k. So we are writing like this. Why we are doing it? We will understand. When we take the differentiation dy dx or dy dx, this power, this summation will never change because it will be uh, some way accommodated in the m. So you don't need to change. This is one of the advantage. And then solve for whatever the differential. You put these things in the actual OD and solve for it. How much you will reduce. Then go for the first step, that is check for the lowest order. X to the power m minus 1 must be the lowest order. Sometimes it can be m minus 2 also. Okay, go for the lower order. Put k is equal to 0. Check which is the lowest order x possible. Equate its coefficient to 0 with that k value. And you will get some value of m. If it is equal or if it is unequal, we have a different set of solutions. We have seen it. Okay. Then go for the next order term, try to relate a relationship, and then go for a generalized relationship, which is easy. Just changing the k value, right? And get your recurrence relation, find out the y, and while finding out the y, you have x to the power m. Put the value of m. If m1 and m2 are different, so there are two different solutions. If they are same, then the second one will be differentiation with respect to m, not with respect to x. So it will give you some log x kind of. So this is what you have got. Okay, and distinct roots we have already seen. Okay, and the best application of this is that this Frobenius method is helpful in solving different Legendre polynomial, Bessel polynomial, and Hermite differential equations to get the Hermite polynomial, which is extremely important in quantum mechanics and in many other fields of physics. Okay, so this is the biggest application of the Frobenius method, and one such is discussed in the Week 8 content. So with this, I would like to end, and it's all the best for your exam. Thank you.